Hey everyone, in this video I will go through the code of Mistral 7B fine-tuning. So first you need to install the relevant libraries and these are all the common stuff you can imagine. That is accelerate bits and bytes for applying QLORA and for quantizing the model so that you can accommodate the entire model in a single GPU and do the fine-tuning rather quickly. Then a PEFT library, of course, and datasets and TRL. And then the first thing, the code that you see here is quite standard code in many production grade fine-tuning code bases that you will find, and which applies to most of the open source model that is used for fine-tuning nowadays. And it starts with these script arguments where we have a bunch of parameters defined, and these are all defined within a single class. So let's quickly go through them. For example, this one, per device train batch size. So here I have kept it at 4, and depending on the power of your GPU, you may have to keep it lower this number. So this one, this one. So when I have set it to a number 4, and for example, you have just single GPU, that is one GPU, then your total effective batch size for the entire training will be 4. And if you have 4 GPUs, then the total effective batch size for the entire training will be 4 multiplied by 4, that is 16. So that's how this is calculated. And then I come to this one, per device eval batch size, which is exactly the similar concept like the train batch size. And then gradient accumulation steps. So this is the number of updates steps to accumulate the gradients for before performing a backward or update pass. Then coming to these parameter local rank. So in the context of distributed training, a single training job is split across multiple processes, often spread across multiple machines or nodes and multiple GPUs. And each process running a piece of the training task is assigned a unique rank to identify it. The local rank parameter is specifically the rank of a process within a single node. That's what it represents. So to give you an example, imagine you have 2 nodes, each with 4 GPUs, making it a total of 8 GPUs. The global rank would be an index from 0 to 7 to uniquely identify each process across both nodes, and the local rank would be an index from 0 to 3 in that case for each node to identify which GPU is being used for the current node. So the use of local rank becomes particularly important in strategies like distributed data parallel or DDP in PyTorch. DDP uses local rank to partition the mini batch across the multiple GPUs on a single node. And why it defaults to -1, that is the one that you see. So when local rank is set to -1, it generally means that the training is not being run in a distributed environment. The framework would then default to using all available resources on the single machine you are running the training job on. And then you have learning rate. This is pretty obvious. And another one, next one is max grad norm. So when backpropagation is performed, each parameter's gradient is computed. These gradients indicate how much the loss function will change if the parameters are adjusted by a small amount. In some cases, especially in recurrent neural network and deep networks, these gradients can become very large, leading to what is known as exploding gradients problem. So gradient clipping is the technique to prevent gradients from becoming too large during the training of neural networks. So to do that, if we consider the gradients as vectors, the idea behind gradient clipping is to scale down the gradients if their L2 norm exceeds max grad norm. So that's the number that we are setting here. That is 0.3, which will control at what level the gradient clipping would be applied. And the idea of gradient clipping is very simple. If the gradient gets too large, we rescale it to keep it small. All right, then moving forward, all these parameters use 4-bit, use nested quant, etc. These are parts of the bits and bytes config that I will come in a second. So let's just move forward for now. And there are some other as well. Some of them are quite obvious. For example, gradient checkpoint, that's a Boolean parameter. And I definitely suggest just quickly go through Hugging Face documentation, because it's all these parameters are very, very well defined in the documentation. All right. And then after I defined these entire class subscript arguments, then to actually apply and invoke this class, I can have these two lines, that is HF argument parser and then parser.parse args into data classes. But this will be applicable if you are running in a Python file, that is, you are executing an actual Python file, which is the most regular and normal case if you are running this code in your production. But here I have kept these two lines commented out because this is a Jupyter Notebook environment and these argument parser will not really work correctly. But anyway, just to know what they are. So this HF argument parser class is provided in Hugging Face's transformer library. This class takes one or more data classes and turns their data attributes into command line attributes or command line arguments of an argument parser object. That's the whole job here. Okay, so but anyway, I'm keeping it commented out here. So instead, because it's a Jupyter Notebook, so what I'm doing, I'm just using another variable script args, which will, and then just manually defining each of the parameters values. So script args is I'm using the original class and then just give the numbers for each of the parameters. All right. And crucial thing is the model that I'm using here is Mistral 7B instruct v01. So this is the instruct version of the model. And the dataset that I will be fine-tuning on this model is Python code instruction 18K alpaca. It's a very famous dataset. I will show you what the dataset contains in a second. So yeah, that's the so all these parameters are defined with this script args variable. So each time I want to use any of these values, I just do, for example, script args dot weight decay and similar couple of things. All right, so this is the dataset that I'm going to use for this fine tuning. And so you can see there are instruction column, input column, output column, and then the all important prompt column. So if you just click on any of this row, you will get to expand it. So this prompt column is actually holding all the relevant information that I need, but I need to make some formatting changes for this prompt column, because a Mistral 7B has a very specific requirement, and let's actually go through that. So this is I have put the instruction here. So Mistral 7B instruct, that is a model that I'm going to use. It's recommended to use a following chat template. So my template needs to start with these S, then inst, then your actual instruction, then another this particular format, that is a square bracket and / and another inst, then your model answer, then again an S, and then again inst, and then your follow-up instruction, and then again inst. So this, if you are familiar with large language models, you will be, this is actually quite easy. Each model has their own particular prompt requirement when that is very important, either for inferencing or while you are doing fine-tuning. So here these S and the ending S, these are special tokens for beginning of string, BOS, and end of string, that is EOS. And while this inst, this particular string here, is just a regular string. And so my job now is to change the original data frame that we just saw, that is the Python code instruction 18K alpaca, to this particular format. And hence I have this gen batch train, this util method. So let's quickly go through this part of the method. Initial parts are just the normal ones, that is I'm loading the data set, then making the total samples, taking the 10,000. And also you need to assign a validation percentage so that your train and validations are completely different. And let's start the iterations, the looping through the data set. So for when the counter is more than train limit, because we only do this whole calculation only for the up to the train part of the data set. And just don't forget this part, that this is our original data frame, that is the original data set is in this particular format, and I will be working only with this prompt, this particular column data, because that has got all the necessary part that I'm going to need. So here in this loop, I'm just going through row by row. So let's go. This is like the first row that I'm working with. So first I need to extract the original prompt, and for that I'm kind of removing this part of the string, and also Python code this part of the string by replacing them with an empty string. And then the next one, that is this line, instruction start. So here this line is finding the start index of the actual instruction in the original prompt. First original prompt.find, then this instruction. This will locate the index where the substring instruction begins, and by adding this part, that is length of this particular string, the code is effectively moving the start point to the end of the substring, that is to the beginning of the actual instruction content. And if you look at the original data format, it will become clear again. That is so you can see that instruction is starting here, and what I'm interested is that I need to remove this part, and I'm interested only with the actual instruction, which is create a function to calculate the sum of a sequence of integers. This is actual instruction, and then again start other stuff. And instruction end, this is will just find the end index of the instruction part by locating where the where this output, this string, this substring begins. So this essentially marks the boundary between the instruction content and the output or response that follows in the training data. And finally, the actual instruction, that is this line is just this substring represent the instruction part of the prompt. So I'm also applying the strip method, which will remove the any leading and trailing white spaces characters from the extracted instruction. And then content start, this line is identifying the starting index of the actual content or output part of the original prompt. This is done by finding the index of the substring triple hash output, and then moving past the substring using the length of this particular string. Just this is exactly similar to what was done previously with the instruction start, this one. And finally, the content is original prompt content start, this line right here. So this extracts the output or content part of the prompt starting from content start to the end of the original prompt. And the strip method again ensures any extraneous white spaces at the beginning or end of the content is removed. And then this new text format, this is just formatting my instruction and content exactly as required by Mistral 7B model. That is, I need to append these part to my instruction, and also append this part to the instruction. Okay. And finally, I'm yielding. Okay, I'm also tokenizing it here by invoking my tokenizer, which we have defined earlier. And if not, I think I will define it in the next cell. And then finally, yielding the text and the new text format and increasing the counter. And thereby, this whole loop gets executed, and it will go through row by row for the entire data set. And I have the exact same util method for my validation batch as well. It is absolutely no difference. It is just for the validation. Okay. And yeah, next is the util method, which will actually prepare my model with all the LoRa config and BNB config and PEF config, etc. So yeah, so I will go through quickly with these bits and bytes config. Let's quickly go through these individual parameters here of the bits and bytes config. So the first one, load in 4-bit. This parameter is for loading the model in 4 bits precision. This means that the weights and activations of the model are represented using 4 bits instead of the usual 32 bits. This can significantly reduce the memory footprint of the model. 4-bit precision models can use up to 16x less memory than full precision models and can be up to 2x faster than full precision models. However, if you need the highest possible accuracy, then you may want to use full precision models. And the next one is BNB 4-bit use double quant equal to true. This parameter enables double quantization, or also called nested quantization, which applies a second quantization after the initial one. It saves an additional 0.4 bits per parameter. And then the next one is BNB 4-bit quant type equal to NF4. This parameter specifies a type of 4-bit quantization to be used. In this case, NF4 refers to normalized float 4, which is the default quantization type. And the last one, BNB 4-bit compute D type equal to torch.float16. So this parameter determines the compute data type used during the computation. It specifies the use of the bfloat16 data type for faster training. The compute type can be chosen from options like float16, bfloat16, float32, etc. This configuration is needed because while 4-bit bits and bytes stores weights in 4 bits, the computation still happens in 16 or 32-bit. And here, any combination can be chosen by the user, that is by the developer. And the options are float16, bfloat16, and float32. And here I've chosen float16. And the matrix multiplication and training will be much faster if one uses a 16-bit compute D type. And the basic question you may ask is, does floating point 4-bit precision quantization needs any special hardware, or has it any hardware requirement? Note that this method is only compatible with GPUs, hence it is not possible to quantize models in 4-bit on a CPU. That's the only requirement. And among the GPUs, there should not be any hardware requirements about this method. Therefore, any GPU could be used to run 4-bit quantization as long as you have CUDA version equal to 11.2 or more installed. And keep also in mind that the computation is not done in 4-bit. The weights and activations are compressed to that format, and the computation is still kept in the desired or native D type. So let's quickly go through the various parameters of LoRa config. I have already discussed in detail this one, target modules, as to why I need that, etc. Now, the next one, hyperparameter, is R. So R represents a rank of the low rank matrices learned during the fine-tuning process. As this value is increased, the number of parameters needed to be updated during the low rank adaptation also increases. So intuitively, a lower R value may lead to a quicker, less computationally intensive training process, but may affect the quality of the model thus produced. However, increasing R beyond a certain value may not yield any discernible increase in the quality of the model output. And the next one is LoRa alpha. So this parameter is used for scaling. So according to the LoRa research paper, the original one, the updated weight delta W is scaled by alpha divided by R, where alpha is a constant. When optimizing with Adam, tuning alpha is roughly the same as tuning the learning rate if the initialization was scaled appropriately. The reason is that the number of parameters increases linearly with R, and as you increase the R value, the values of the entries in delta W, that is weight updates, also scale linearly with R. And we want delta W to scale consistently with the pre-trained weights no matter what the R value is used. That's why the author set these alpha parameter to the first R and do not tune it. The default of alpha value is 8. And then I have these dropout rate. So this is the probability that each neuron's output is set to 0 during training. used to prevent overfitting. So dropout is a general technique in deep learning to reduce overfitting by randomly selecting neurons to ignore with a dropout probability during the training. The contribution of those selected neurons to the activation of downstream neurons is temporarily removed on the forward pass, and any weight update are not applied to the neurons on the backward pass. The default value of LoRa dropout is 0. And then I have this bias parameter which can take any of the values between none, all, and LoRa only. If all or LoRa only is used, the corresponding biases will be updated during the training, and the default value is none. And lastly, I have this task type. So this is generally just represent the type of task that the model is being fine-tuned for. That is all. So possible task type include causal LM, feature extraction, a question answer, sequence to sequence LM, sequence classification, and token classification. So these create and prepare model then finally prepares my all the quantization parameter, that is bits and byte and peft config, and finally from this entire util method I'm returning model, peft config, and tokenizer. All these three things we will be using in the next cell where I'm defining all the training arguments. Alright, so the training arguments, almost all of these parameters are coming from our script args that we have defined at the very top right here. That is, these are part of our script argument class. And then we define the script arguments variable by actually manually specifying all the parameters. And we have already discussed about this. So let's move on. So after this training argument is defined, I am just invoking or executing this create and prepare model, which will give me my model, peft config, and tokenizer. And let's quickly check out the model. So once I get the model, so this is the model structure that we have for this fine tuning. And we can see that the attention, the self-attention layer here, and this is the target modules that we actually used while defining the bits and bytes config, and these are the ones qproj, kproj, vproj, etc. And then before actually starting the training, I obviously have to define my train gen and val gen, that is a training dataset and a validation dataset, by invoking or applying these gen batches train and gen batches validation method that we have defined earlier. And both of these methods, as we already discussed in detail, they are just pre-processing or preparing the actual training data to be worthy of Mistral 7B fine-tuning, because we need in a particular format for Mistral 7B as required by the model. And with that, we are almost done. This is pretty much the last step, because actually running the training. So you define this particular thing you have to do. I got it from some other repos. Other people have faced some issues with FP16 training, because we are using quantization. That is, we are not doing the training with the full precision of FP32. Instead, we are using FP16. And for that, you kind of, many people have used this particular configuration for the tokenizer to go the training in the right way. And trainer, this is just, I'm just implementing my SFT trainer with all the parameters defined. And here the parameters are quite so simple. Model is model, train dataset is my train gen, and peft config is coming from the previous peft config that we have got after executing this method, create and prepare model. Alright, so with that, you define the trainer, that is with all the parameters of the trainer, and then you simply run trainer.train, and it may take a couple of hours depending on the power of your GPU. And yeah, so that's pretty much a very production grade code for fine-tuning Mistral 7B. Thank you very much for watching. Do stay tuned, because I plan to do quite a few LLM related and fine-tuning related videos over the coming weeks. So see you in the next one.